Good afternoon, all. Dr. Bijul, good afternoon.
Good afternoon.
Can we start the talk?
Sure. Please go ahead.
Yeah, thank you.
Good afternoon to one and all present here. It gives me immense pleasure to welcome you to the 23rd talk of the Transpedia Research Talk Series organized by KSCSTE National Transportation Planning and Research Center, NATPAC. This talk series is yet another unique venture of NATPAC designed to explore diverse topics from cutting-edge technologies to sustainable solutions. Here, we will be featuring eminent young researchers to share their valuable insights for kindling the spirit of future research and development in transportation. Today, we have with us Dr. Bijul Raveendran, former research scientist, Indian Institute of Technology, Bombay, for sharing his valuable insights on the topic, counting down to safety, evaluating countdown timers at intersections. Now, I request Sri Arun Chandran, senior scientist, to deliver the welcome address.
Thank you, Panchamai, and good afternoon, all. KSCSTE-NATPAC has launched a technical discussion series called Transpedia Talk Series, which is envisioned to promote research for shared benefit by disseminating knowledge on diverse topics from cutting-edge technologies to sustainable solutions. Desirably, this also brings out a platform for young researchers across the globe to connect and interact to better shape the future of research and develop in transportation. The inaugural talk of the series was conducted on 24th August 2023 in an online platform where more than 200 participants from eminent institutions, departments, etc. attended. The inaugural address was given by Professor Dr. Tom V. Matthew, Chairman, Research Council, KSCSTE-NATPAC, and Professor at IIT Bombay. The 23rd talk in the series will be delivered by Dr. Bijul Raveendran, former research scientist, Department of Civil Engineering, IIT Bombay. It is with sincere appreciation and great enthusiasm that we welcome our distinguished speaker, whose gracious acceptance of our invitation brings immense value to today's proceedings. We look forward to gaining meaningful insights and expert perspective on the topic, counting down to safety, evaluating countdown timers at intersections. After the presentation, we will have a question and answer session where you can pose your questions, or in fact, you can talk to the speaker directly. And thank you.
Thank you, sir, for your welcome now. Now, I would like to invite Dr. Vasudevan N., junior scientist, to introduce the speaker to the audience.
Good afternoon, all. Today we have Dr. Bijul Raveendran, former research scientist in the Department of Civil Engineering, IIT Bombay. Dr. Bijul received his doctorate from Transportation System Engineering, IIT Bombay, under the supervision of Professor Tom V. Matthew and Professor Nagendra R. Velaga in the year 2024. He has more than 6 years of experience at IIT Bombay in handling a wide range of research and industrial consultancy projects related to traffic flow management and road safety. His research interests include traffic signal control, traffic safety, microscopic traffic flow modeling and machine learning models, and connected and automated vehicles. With this note, I welcome Dr. Bijul Raveendran to this talk series. Thank you.
Thank you.
Thank you, sir, for the introduction. Now I invite our distinguished speaker to deliver the talk. Over to you, sir.
Thank you. Thank you very much. Very good afternoon to you all. First of all, a big thanks to NATPAC for providing me with this wonderful opportunity to be a part of the Transpedia Talk series. Without much ado, I'll start the presentation. So the content I'm presenting here today is part of my PhD work carried out at IIT Bombay. At a very broad level, it addresses how countdown timer at signalized intersections impact driver behavior.
Dr. Bijul, can you
are you
hear
able
us?
to see the screen?
Yeah, we can.
The slide
see
is changing, right?
Yes.
Yeah, so sorry about the delay.
Yeah.
So as traffic professionals and road users, you all might have come across countdown timers at traffic junctions. They're used across many intersections in Kerala. Countdown timers are auxiliary devices installed at signalized intersections to help drivers make informed decisions. Although they are primarily aimed at improving throughput, they affect both safety and efficiency at signalized intersections. So my presentation contains an introduction to the topic, the framework of the study, the 4 objectives that I'm addressing today, and the presentation concludes by discussing the outcomes and listing the major contributions. Studies show that countdown timer affects stop and cross behavior at the onset of yellow. This points to potential anticipation of signal change in the presence of countdown timer. Such an anticipation could affect how drivers execute their stopping or crossing. This could also impact drivers' indecision as they stop or cross. This anticipation could also lead to variation in rear-end collision potential during the signal transition phase. Now, rear-end collisions are one of the major types of conflicts at signalized intersections. However, there are no detailed studies that explore the effects of countdown timer on potential collisions. While these 2 points address driver behavior during the signal transition phase, the next point is related to green phase or Q discharge. There is a potential spatiotemporal variation in driver behavior in the presence of countdown timer. The existing analytical car following models that simulate vehicle discharge do not consider anticipation or such spatiotemporal variations. Finally, studies have generally shown that countdown timer improves safety and efficiency of signalized intersections. Now, another way to improve intersection efficiency is using an adaptive traffic signal control that adapts to the variations in traffic. However, countdown timer is not generally used with adaptive signal control, potentially since the phase durations are not known beforehand. Studies in other areas like vehicle-to-infrastructure communication and adaptive cruise control have shown that informed decisions positively impact the performance of adaptive traffic control. Hence, countdown timer, which helps drivers make informed decisions, could potentially improve the performance of adaptive traffic control. So, based on these research gaps, this presentation addresses 4 specific objectives. The first objective is modeling the impact of countdown timer on drivers' anticipation at the onset of yellow, followed by modeling the effect of countdown timer on rear-end collision potential during the signal transition phase. The third objective is modeling the car following behavior during Q discharge at signalized intersections. And finally, the development of an adaptive traffic control algorithm that can be augmented with countdown timer and the subsequent evaluation of its safety and efficiency. To achieve these objectives, a study framework was formulated that first studied drivers' anticipation at the onset of yellow during using driving simulator data. The impact of this anticipation on rear-end collision was then studied using field data. The first 2 objectives were related to the signal transition phase. Then in the third objective, the Q discharge was studied using field data. Finally, parameters related to driver behavior during the signal transition phase and the concept of Q discharge time were utilized to incorporate countdown timer and adaptive traffic signal control. The final objective was carried out using field and VSIM simulation data. Now I'll move on to the detailed elaboration of the objectives. I'll also try to explain the data collection and methodology used in each objective. So moving on to the first objective of driver's anticipation at the onset of yellow. The overall methodology in this objective consisted of a driving simulator data collection, which involves the scenario design and questionnaire survey. This was followed by preliminary analysis and statistical modeling, followed by the validation of results. So we have a few high fidelity driving simulators at IIT Bombay that provide a realistic driving experience and replicate field conditions like ambient traffic and traffic signals. These simulators are capable of providing up to 51 variables as outputs in at every 0.05 seconds. That is at a rate of 20 hertz. The notable outputs from the simulators include the speeds, acceleration, brake pedal force, and so on. So to obtain data for this objective, a detailed driving simulator scenario was developed that contained 3 drives covering 41 signalized intersections. Out of these 41 intersections, 24 intersections were used for data collection. Out of those 24 intersections, 12 had a countdown timer display and the remaining 12 did not. The signal would change from green to yellow as the vehicles approached the intersection at predetermined time to stop line values ranging from 1 to 6 seconds. Overall, 82 participants took part in this driving simulator experiment. And using this driving simulator data, we went out with the analysis of anticipation. So the brake reaction to a signal change at signalized intersection is generally analyzed using BPRT, or a brake perception reaction, which considers the yellow onset or the signal change from green to yellow as the trigger for the braking action. However, in the presence of countdown timer, the drivers anticipate the signal change and sometimes brake even before the onset of yellow. So to account for this anticipated braking, we proposed an alternate called brake initiation with respect to the onset of yellow, or BIY. By analyzing BIY values, we were able to establish the anticipation in the presence of countdown timer. So if you see the graph here, we can just a moment. Okay. If you see the graph here, you can see that in the absence of countdown timer, the frequency of BIY is spiking at about 1 to 2 seconds after the onset of yellow, showing that yellow onset indeed acted as a trigger for those braking actions. Whereas in the presence of countdown timer, most of the braking actions are happening before the onset of yellow, and the curve is much more flatter, pointing to anticipated braking from the drivers. This anticipated braking also meant that drivers had much lower speeds at the onset of yellow in the presence of countdown timer. These factors also enabled drivers to come to a stop with much lower deceleration in the presence of countdown timer. They were able to brake early, which gave them much more time to execute their stopping decision, and they could come to a stop at much lower or deceleration, or with a much smoother braking action. Now, on the contrary, it was also observed that countdown timer increased the speeds while the vehicles were crossing the stop line. There was a small but significant increase in the speeds in the presence of countdown timer. So based on the insights from these analysis, we developed 2 distinct accelerated failure time models, the first of which was for the duration of braking. So earlier we found that the drivers braked early, which also translated to an 88% increase in the time that they had to execute their stopping distance, which again meant that they could come to a stop with much smoother braking action in the presence of countdown time. Now, the second AFT model was for the time taken to cross the stop line. So earlier we saw that the vehicles crossed the stop line with higher speeds in the presence of countdown timer, which also meant that they executed their crossing maneuver 21% faster than in the absence of countdown timer, 21% faster in the presence of countdown timer than in countdown timer's absence. So based on the insights from the anticipation in the presence of countdown timer, we moved on to the second objective, that is analyzing the rear end collision potential during the signal transition phase in the presence of countdown timer. So for this objective, we used field data. Videographic data was collected from 3 intersections, out of which 2 were four-linked intersections and 1 was a T intersection. All these 3 intersections were from Kerala. The traffic at these locations was predominantly two-wheelers and cars. And once the traffic data was collected using two different cameras, one for capturing the traffic and the secondary camera for capturing the signal control and the countdown timer information. And the data was clubbed together later on. And detailed trajectory data was extracted using the IATB traffic data extracted. And the final data set contained the vehicle IDs, the vehicle types, the trajectories, timestamps, the turning movements, the countdown timer information, etc. So this is the overall methodology adopted in this objective. First part is the data preparation, where the data is collected and data is extracted, as I mentioned, as I explained earlier. And from that extracted data, some MATLAB codes were developed to identify leader-follower pairs. And this was followed by the analysis and modeling. The first step of which was computation of modified time to collision. This was followed by analyzing how countdown timer impacted the spatial and temporal distribution of rear-end collision. And finally, the detailed modeling to quantify the impact of countdown timer on rear-end collisions. So modified time to collision, which is used in this analysis, the surrogate safety measure used to compute conflicts. The definition of MTTC would be, it is a time until two vehicles collide, provided they maintain their heading, acceleration, and speeds. This is a very reliable measure for rear-end collision analysis in both simulated traffic, simulated data, and real traffic data. So the descriptive statistics of the trajectory data are shown here. The most notable aspect here is the correlation between driving simulated data and field data. For example, there is a reduction in speed at the onset of yellow in the presence of countdown timer for both the simulator and field data. And similarly, the trend is same for all the other parameters. And finally, the MTTC values were computed for with and without countdown timer scenarios. All MTTC values less than 3 seconds were considered as potential collisions. And these MTTC values were further subdivided into three different distinct categories. The first of which was MTTC less than 1 second, which is also the most severe of the conflicts shown here. The other categories were MTTC between 1 and 2 seconds and MTTC between 2 and 3 seconds. All MTTC values greater than 3 seconds were considered as no conflict scenarios here. So coming on to the first analysis of the temporal distribution of rear-end collisions. To quantify this, you can see the plot here. This shows the frequency of modified time to collision for all collisions, that is MTTC ranging from 0 to 3 seconds for the last 6 seconds of green and for the entire duration of yellow. So it can be seen that for the last 3 seconds of green and the entire duration of yellow, there is a significant reduction in the frequency of modified time to collision in the presence of countdown timer, pointing to an improved decision making from the drivers during the signal transition phase in the presence of countdown timer. Now, the next plots show the same parameters, the frequency of MTTC for the three subcategories. And the most notable improvement in the presence of countdown timer is for MTTC less than 1 second, which is also the most severe of the conflicts, which points to a very significant positive impact of countdown timer on the temporal distribution of rear-end collisions. This was followed by the spatial analysis of the spatial distribution of rear-end collisions. So here what you see is a heat map. So here the x-axis shows the length of the queue starting from the stop line, 0 being the stop line, and queue is considered for a length of 100 meters. And the y-axis represents the width of the road, such that 0 represents the curb side and the highest value represents the median side. The dashed vertical lines you see here are the extent of dilemma zones, the start and end of dilemma zones. So it can be observed that in the presence of countdown timer, the dilemma zones were slightly shorter and more closer to the stop line, whereas the conflict zones were shorter, but they were far away from the stop line. So the other three sets of plots show the same spatial distribution of variant collision for the three subcategories. So as we show, so in the previous analysis, temporal analysis, we can see here also that there is a significant improvement in the presence of countdown timer in the spatial distribution of variant collisions. Now, with these insights, we went on to develop a model to quantify how countdown timer improved the variant collision potential at signalized intersections. For this, we considered the three subcategories of modified time to collision, and we considered the no conflict scenario, or MTTC greater than 3 seconds, as the reference category. And it was observed that there was a very significant improvement in the presence of countdown timer for all the categories. And it was particularly notable in the MTTC less than 1 second category, which represents the severe collisions. This again reinforces the finding that countdown timer significantly improves variant collision potential at signalized intersections. So with this, I'm moving on to the next objective of modeling car following behavior during queue discharge at signalized intersections. So the most notable impact of countdown timer during queue discharge is on startup loss time. Startup loss time is the extra time that the first few vehicles in the queue take due to delays such as reaction delays and acceleration delays. There are numerous studies that show that countdown timer significantly reduces or eliminates startup loss time. This study instead attempted to model the car following behavior during queue discharge by incorporating the effects of countdown time. So first of all, just a background on what a car following model is. A car following model describes how a driver adjusts their movement based on the behavior of the vehicle ahead of them. So there are numerous car following models like Weidemann models, which are used in VISIM, the very popular intelligent driver model, or IDM, Gibbs model, and so on. Most of these analytical car following models have some underlying mathematical equation that do not capture the effect of countdown timer, like anticipation and indecision that are introduced by the process of countdown timer. So this necessitates the development of a data-driven car following model capable of capturing such variations in the presence of countdown time. So with this in mind, we propose using a long short-term neural network model, or LSTM, for modeling the car following behavior in the presence of countdown time. So a typical analytical car following model, say like IDM, would consider variables like speed of follower, speed difference, and spacing, etc., to predict the acceleration or the spacing in the next time step. So for developing this long short-term memory neural network, we had to identify additional variables that would effectively capture the impact of countdown timer. And we identified three such variables, namely the distance from the stop line, the time remaining in the phase, and vehicle class. And the developed IDM model contains all the 6 input variables shown here. And it gives 2 output variables, which are the spacing and the lateral movement in the next time step. Now, on to the right, you can see the structure of the LSTM model, showing the inputs, the layers, and outputs. Now, apart from model calibration, LSTM also requires the calibration of parameters like a number of layers, a number of neurons, learning rate, etc. This was carried out by sensitivity analysis. So once the LSTM model was calibrated, its results were compared with outputs from a calibrated intelligent driver model, and the results are shown here. It can be seen that LSTM performed significantly better than IDM in predicting the following behavior. Now, these are some sample plots. This is a sample trajectory from the model that we developed. Here you can see the ground truth, the actual data, and the predictions made by IDM and LSTM. And you can see that LSTM is able to predict much better than IDM. It stays close to the ground truth. And this is a sample leader-follower pair interaction represented in the same way. Here again, you can see that LSTM is able to recreate or predict the following vehicle's movement much closer to what the ground truth is. So with insights from the anticipation, the radon collision, and the idea of queue discharge, we now address the final objective, or the incorporation of countdown timer in adaptive traffic control. So, an adaptive, just to give a background on adaptive traffic control system. An adaptive traffic control system is a type of traffic control that adjusts signal timing in real time by responding to actual demand. So there may be sensors like loop detectors or cameras that capture the traffic demand, and there'll be some underlying optimization technique or some heuristic algorithm that governs the operation of this adaptive traffic control. And they are known to reduce delays, stops, and queues. There are many notable adaptive traffic control algorithms out there, like Scoot, SCATS, and so on. And one notable Indian example is KSCSTE-NATPAC, developed by CDAC, and it is implemented. It is active in many Indian cities right now as we speak. So the overall methodology for incorporating countdown timer in adaptive traffic control was first was to develop an adaptive traffic control algorithm based on queue length that will be able to take a countdown timer into their framework. And the second part of the methodology was the independent evaluation of this adaptive traffic control. The third step was the actual incorporation of countdown timer into that adaptive traffic control framework. And finally, the evaluation of incorporation of countdown timer in adaptive traffic control by looking into their efficiency and safety performances. So the main backbone of this adaptive traffic control logic that we developed here is queue discharge time, which is essentially the time required to clear a queue of non-length. It sort of assumes AX plus B kind of relationship between discharge time and queue length, where A is the term corresponding to saturation headway, and B is the term corresponding to a startup close time. So this is the overall adaptive traffic control logic. So using the queue discharge time, which I mentioned earlier, the algorithm computes a parameter called the projected cycle length, or PCL. So PCL is the time it would take to clear the projected queues on all the phases for one cycle. For example, assuming a simple 4-phase signal control, and assuming that the signal control algorithm is about to serve the first phase for P1, the algorithm already knows the green time allotted to phase 4, because phase 4 has just concluded. So we know how much green time was allotted to phase 4. So we can compute the green time required for P1 using the queue discharge equation we saw in the previous slide. And the algorithm then linearly extrapolates the existing queue lengths on P2 and P3 to determine the length of queues on P2 and P3 by the time those phases will have to be served green. The extrapolation is based on the time taken for the present queues on P2 and P3 to accumulate. The PCL is essentially the sum of the computed or projected green durations for all the 4 phases, and the yellow durations and all red durations as well. The PCL thus computed is compared with the threshold value, and if it exceeds the threshold, green time for P1 is proportionally adjusted. And then this computation PCL is carried out at the beginning of each green phase. That is the basic idea of this adaptive traffic control logic that we have developed in the study. So next step was to simulate the effects of countdown timer into this adaptive traffic control framework. So this was carried out using this adaptive traffic control algorithm was implemented in Visim using the MATLAB COM interface. And the typical characteristics of with and without counter timer scenarios were implemented by calibrating by developing two different models and calibrating these models with data from the intersections that contain countdown timer for the first model and did not contain countdown timer for the second model. So additional vehicle characteristics like vehicle composition, speeds, etc. were also incorporated, and the reaction to amber was updated. And finally, the car following model was calibrated in detail during using a genetic algorithm and the MATLAB COM interface at trajectory level. And once this countdown time was incorporated into the adaptive traffic control framework, we moved on to the its evaluation. The first part is the evaluation of its efficiency. So here we considered two key performance indicators, average stop delay and average queue length. And we observed that there was a significant improvement when adaptive traffic control was incorporated with countdown timer. So the three different simulations that are compared here are: one is the vehicle actuated control, which sort of served as a benchmark for evaluating the adaptive traffic control. The second one is adaptive traffic control without countdown timer, and finally the adaptive traffic control which has been incorporated with countdown timer. So you can see clearly that there is an improvement. There's a marked improvement when adaptive traffic control is incorporated with countdown timer. The next is the evaluation of the safety of adaptive traffic control incorporated with countdown timer. So we considered different parameters like the length of type 2 dilemma zone, the red light violation, and sudden stopping, etc. And similar to the previous evaluation of efficiency, it was observed that adaptive traffic control incorporated with countdown timer improved the performance significantly. So to conclude, this study addressed 4 different objectives related to queue discharge in the presence of countdown timer. The first of which was drivers' anticipation as they stopped or crossed at the onset of yellow. So we proposed a new metric called brake initiation with respect to the onset of yellow, and we saw that there was significant changes to speeds, decelerations, and braking behavior, and there was an anticipation in the presence of countdown timer while they braked and tried to pass through the intersection. Then we modeled the duration of stopping and crossing to establish these findings. This second objective built on the first objective and tried to model the rear-end collision potential during the signal transition phase. First, the spatial and temporal distribution of rear-end collisions were analyzed using modified time to collision, and then the rear-end collision potential was modeled. The third objective, we tried to see the variations in driving behavior during queue discharge by developing a data-driven car following model. And using the inputs from the first 3 objectives, we incorporated countdown timer in adaptive traffic signal control, for which we developed a queue length-based adaptive traffic control algorithm. And we saw that the incorporation of countdown timer improved safety and efficiency significantly. So the major research contributions from this set of studies is that first one on drivers' anticipation. It showed that the impact of countdown timer on drivers' anticipation at the onset of yellow can be established by analyzing and modeling driver behavior parameters. In the second objective related to rear-end collision, we could see that analyzing the spatial and temporal variations and modeling its probability can determine countdown timer's influence on rear-end collision during the signal transition phase. And in the third objective, we were able to develop a data-driven car following model that took into consideration various additional impacts of countdown timer, like vehicle class specific variations and spatial temporal variations, etc. And finally, we found that countdown timer can be incorporated into adaptive traffic signal control using queue discharge time to improve its safety and efficiency. That concludes my presentation today. Thank you very much.
That was nice presentation. Thank you, sir. Now the forum is open for discussion.
Okay, Dr. Bijul, it was a very nice presentation.
Thank you.
This is Praveen from NATPAC. I would like to know a couple of things, like just some queries, like was the influence of volume taken into account, like when the queue length is increasing, or say during peak and off-peak time, etc. Was there any influence of that on the rear end potential collisions, or also the impact on countdown timers? Was that accounted?
We did not specifically look into that. The main reason being, when collecting data, you might have seen at intersections, when the volume is very high, the policemen resort to operating the signal manually. And when they are operating the signals manually, the countdown timer display will not be available. So we could not actually collect data in very oversaturated conditions. So the straight answer would be we did not do a detailed analysis on how the rain collision potential would vary when the traffic is varying.
Okay, just one more thing, like you are basically focused on cars, or is it that you are taken the average of different categories of vehicle, or like that? Because at a signal, more or less it will be a mixed traffic, right? So
Yes.
how was that accounted?
For the first objective, where I used driving simulator data, only cars were considered. For all the other objectives, all vehicle classes were considered. So I had done some vehicle class specific analysis as well, but I could not present all the results here because of lack of time. But straight answer would be for the first objective, only cars. For all the other objectives, all vehicle classes.
Okay, so I like to know one more thing. Like, so it might be like the acceleration deceleration characteristics of different vehicles will be different. So
Yes.
like it's accounted in the model, right?
Yes, that is correct.
Okay.
As you
fine.
said, the acceleration behaviors were significantly different for the vehicle classes, and they have been accounted for in the different models that we developed.
So it means that it was taking care of the composition with respect to that thing, right? Or was it an average value which was fed into the model, or like based
actually,
on the
which model are you talking about? The car following model or?
Yeah, which was modified so as to simulate in the adaptive condition.
Yeah, okay. Okay. So we consider different vehicle classes, and for calibrating, within calibration, we have to input different parameters, right? So different vehicle classes were used, and their acceleration parameters were given as inputs.
Okay, fine. Okay, thank you.
Thank you.
Hi, Bijul. Any modification for the lost time estimation? Because
I believe we are talking about the adaptive traffic control.
no. In case of a timer, you expect the lost time to be minimal, no?
Yes, that is correct. So the issue with modifying the lost time is that are you talking about the ordered interval, or the?
No. In the maybe in the signal design, in the signal design. So we are considering the lost time also. So with the with the signal timer, you are modifying the signal design with the timer, or you're proposing
all the lost time, like all the times and all, we did not tinker with that, because that will have other safety implications when implemented on the field, right? So the queue discharge time, of course, got affected by the presence of countdown timer, but the lost time we decided to keep as such, constant for both the models. Thank you.
Good afternoon, Dr. Bijul.
Good
I
afternoon.
have a question. So what are the difference in effectiveness of this countdown timers across different types of intersection, like roundabout or signalized things?
Roundabout was not taken into consideration. We considered two different geometries, that is four-legged intersections and T intersections. And it was observed that the speeds were significantly, the countdown timer impacted the speeds of crossing more significantly at four-legged intersections. They were not that significant at T intersections. And the same goes with deceleration as well. The main reason here would be that at these T intersections, irrespective of the countdown time, process of countdown timer or the actions, the vehicles anyway, they have to decelerate because they are going to make a turn. So that sort of contributed to reducing the effect of countdown time overall. So the roundabouts were not taken into consideration for the analysis. Thank you.
Thank you.
If I may, hello.
Hello.
Yeah, please,
Uh,
please.
Yeah, I'm Mithun from NATK Surathkal.
Hi.
And it was interesting listening to your presentation. Just had a couple of queries. So the first
Please.
one was in the consideration of a TTC. You have taken a threshold of 3 seconds.
Yes, yes.
So, how do you justify the adoption of a 3-second threshold?
This was mainly done based on existing studies. So our code books don't give a clear threshold for modified time to collision. However, it gives 3-second threshold for TTC, time to collision. And other studies on modified time to collision have generally adopted a 3-second threshold. So we decided to go with that existing studies. And based on that, we did some kind of sensitivity analysis to see how these different thresholds are working out. And we did some basic plots and finally decided to go with a 3-second threshold. We finally decided that 3-second threshold will be significant. So another detailed way could be using some clustering analysis and all. But for this limited amount of data, we felt that going with the literature would be fine.
Yeah, because I've seen many literatures where such kind of an assumption is taken, because the entirety of whether the collision would occur or not, it depends on that specific value being adapted.
Yeah, at a very ideal stage, as you mentioned, we have to go with some detailed analysis like clustering or some other means to exactly pinpoint where the threshold would be. But
yeah,
here, we decided to.
Perfect. What I've seen in many of the literatures of work done abroad is like they are backing their adoption with respect to the accident statistics, which unfortunately we don't have.
No, we.
Good record.
Yeah, right. Yeah. Actually, I tried to get some accident data to compare with what we observed. But there is accident data. But the problem with this specific analysis is that we will not be able to pinpoint the location of the data. That is, how distant from the stop line that accident happened, or what time of countdown that happened, etc., which is very difficult. So we had no ground truth or benchmark to compare it against. So unfortunately, we had to, yeah.
I also do understand, and I used to ask the same question to everyone who presents on this, because I also am trying to find out how to fix up that particular value as a threshold. Another thing is I think someone has already pointed out, when you have multiple follower leader interaction happening, how do you clearly identify and model when it comes to car following?
See, we used LSTM model, which is a data-driven model. So in that, one of the variables was vehicle class. So what the vehicle class would be. And based on that, model itself would learn what the interaction would be if say the following vehicle is a car and leading vehicle is a two-wheeler, what the interaction would be, and so on. So the basic answer would be that we considered the vehicle class as one of the variables, input variables in the data-driven model.
Okay, thank you.
Dr. Bijul, we have Srinivas Sassakat sir with us. Sir, good afternoon, sir.
Good morning, sir.
Kakat sir.
Hello.
I think.
Vasu, we have.
Hello, are you able to hear me?
Good morning, sir.
Yes, sir.
How are you, sir? How are you?
Are you able to hear me?
Yes, sir. Yes. Please go ahead.
Okay, yeah.
Good morning, sir.
Bijul, Dr. Bijul, I was very happy to look at your presentation.
Thank you, sir. How are you, sir?
And very nice to again connect with you with a very good initiative from NATPAC and this KSCST. This is, I think, to be very honest, this is the first presentation after which I'm attending after 3 months, because relatively now it's a free time to attend, and that is the reason and then another motivation for me was I would like to see my own student presentation also. Yeah, so overall it is good to see you. I think good
Yes, sir.
to see you presenting this topic, and definitely this is a very upcoming topic, as well as I can say this is one of the most happening topic. So here you have focused on more on safety. I would also suggest we can also add one more attribute of sustainable transportation in terms of emissions, and perhaps
Yes, sir.
that also can be tested.
Mhm.
So I think some of our research fraternity or scientists from NATPAC, they can take ahead this research, and we should be in position to do something about that also. Of course, the most important challenge here is how to measure it.
Yes.
So we can say that as we can get trajectory data from data from sky or any other trajectory extractor, what we have done. Similarly, there may be also some portable devices which we may place them at intersection with two real implementation design of experiments, and through that we can try to do something about it. And
Yes, sir.
another thing could be maybe additionally we can also see if morning peak hour is going to be different, and toggle mode or evening peak hour. So how much of variability we can also try to understand, also try to incorporate. So these are just my comments. And
Yes, sir.
I just wanted to suggest you also that one can also look at extreme value theory to explore the safety effects for the purpose of assessment, this evaluation of safety.
Mhm.
Is it okay? Am I audible?
Yes, sir. Yes, sir. Yes, sir. You're audible. I was just noting down.
Okay, fine. Just let me. Yeah, these are some of my comments from my side. Thank you so much for remembering me.
Yes, sir. Thank you. It's good to see
Yeah,
you.
otherwise you did a good job, and
Yes, sir.
yeah, it's very nice to see you again. And
Thank you, sir. Thank you.
Vasu has reminded, Dr. Vasudevan has reminded in our group,
Yes, sir.
so I tempted to join again. Sorry, Vasu, you have been always communicating with us, but then somehow we are not getting time. But today it was the day I joined, and I feel very happy, and it's very nice initiative that you are continuing since long. And please continue with this practice. It's a really nice initiative, and it is definitely beneficial to not only the research scholars but whole nation. Well, let's hope that some industry people also will join, and they can take advantage of all this. Thank you so much.
Yes, sir. Thank you, sir.
Thank you,
Thank you
sir.
for comments. Sure, sir.
Thank you, sir. Dr. Bijul, we have a question in the chat box. I'll read it for you. The categorization
Yes.
based on threshold values of MTTC is based on any analysis? Any reason why more effect of timer in category less than MTTC less than 1 second?
The first part of that would be I had explained earlier. Going with the literature and settling on 3 seconds as the threshold of MTC. So for the second part of the question, with the most significant impact of counter timer being on MTTC less than 1 second, MTTC less than 1 second is the most severe of all the conflicts. And the research goes on to show that counter timer has the most significant impact on those conditions, on the conditions that are most severe. So yeah, that is the outcome from that analysis.
Yeah, thank you.
I request.
Any questions from any of the other participants who have joined? Okay.
I request Sri Ashiki Azad, Junior Scientist, to propose the vote of thanks.
Thank you, Panchami. Good afternoon, good evening to everyone gathered here. As we bring this captivating technical come interactive session to a close, it's my honor and privilege to extend a heartfelt vote of thanks on behalf of KSCSTE-NATPAC. Today's session, Counting Down to Safety, Evaluating Countdown Timers at Intersection, was enlightening and thought-provoking. On behalf of NATPAC, I extend our heartfelt appreciation to all those who contributed to success of this event. We are deeply grateful to Dr. Bijul Raveendran for delivering a highly engaging presentation. Your expertise in this subject and the clarity with which you articulated the technical, behavioral, and policy aspects of countdown timers at intersections have added great value to our ongoing discourse on road safety interventions. I would also like to thank our esteemed participants, researchers, and professionals, especially Dr. Srinivas sir, Dr. Midhiman Mohan, and Dr. Ujjwal Solanki, who joined us today. Your presence and active engagement reflect a shared commitment to making our roads safer. A special word of thanks to the organizing team at NATPAC for their efforts in coordinating today's session under the Transpedia Research Talk series. These monthly knowledge sharing platforms are a testament to our dedication to advancing transportation research and policy in Kerala and beyond. By this note, we come to end for today's presentation. Thank you once again for being a part of this session. Thank you all.
Thank you.
Thank you.